Well, the first question is, what kind of decay particle does NP239 emit? Now, it's true, you're looking here, you might think, well, it's 93, that's more than 84, it should be emitting an alpha particle. But if we look at what it decays into, in this case, the atomic number went up by 1, and the atomic mass stayed the same, and that's what happens when you emit an electron. So the answer here would be an electron. That's a 0, by the way. Alright, let's see what we got next here. Let's see, how long did it take for the mass of the sample to be reduced to 50%? So what we do here is, look at the starting amount, it's 60. Half of 60 is 30. So the amount of time it took to get from here to here looks to me to be about, maybe, what would that be, 2 days, is that right? Let's see, I'm going to go 2.5 days. I'm going to say, yeah, it looks to me like it took about 2.5 days. How long did it take to be reduced to 25% of its original mass? Well, let's see. Half of 60 is 30, and half of that is 15, which would be here. And that took 5 days. Let's go on here. Then it says, whoops, what did I just do? Okay, and then how long did it take the mass to be reduced from 50% to 25%? Well, that's 2.5 days. And that's because what is the half-life of NP? Well, it's 2.5 days. Every 2.5 days it gets cut in half. Now let's look at number 6 here. A sample originally had 3.8 grams, and now there's only this much. How old is the sample? Well, here's how we do this. The first thing you got to do is figure out what percent of the parent isotope is remaining. So you take the little number, which is 0.2375, and divide it by the big number that you started with, which is 3.8. And let's see what that gives us. Hang on, I've got to get a calculator. And what that gives me is 0.0625. So that is what percent remains. So now that I know the percent, I come down here and I look at my percent remaining isotope, and here it is right here. And that is the equivalent of 4 half-lives. So I know that there have been 4 half-lives. So the question is, how long does each half-life take? And each half-life, according to what I just calculated, is 2.5 days. I should put a D, days. 2.5 days is how long it takes for each half-life to go by, and there have been 4 of them. So what I do is I say 4 half-lives times 2.5 days per half-life gives me 10 days. Let's look at our next one here. Let's look at number 7. It says we can make this synthetically but does not occur on Earth. Based on this information, why do you think that is? Well, if it has a half-life of 2.5 days, and the Earth is 4.5 billion years old, the problem is all of it has decayed away. Sorry for my terrible handwriting. Number 8. Why would it be worse to handle the sample in the first week? Well, if it's the 2.5 day half-life, so say in 3 half-lives is what we're talking. In 3 half-lives, it will have given up over, the vast majority of its radiation is going to be given off in the first few half-lives. So basically, the reason it would be worse is that most radiation is given off in the first few half-lives. That's terrible handwriting. Look at that, is terrible. Can you believe your teacher writes that terribly? Most of the radiation is given off in the first few half-lives. After that, there's very little left to give off. Alright, let's take a look at this one here. So what I have is Einsteinium is decaying into berkelium. If you notice, that goes from 99 down to 97. That is an alpha particle right there. So it is giving off an alpha particle. I know because the top went down by 2 and the bottom went down by 4. What is the half-life? So to find the half-life, all I have to do is figure out what the starting amount was. In this case, it was 1400. In this case, I'm doing it by radiation counts, but that'll work. I go to 1400. Half of 1400 is 700. I go across, and it looks to me like about 20 days. 20 days. How long would it take for 120 grams to reduce to 15 grams? So the first thing I have to do is I have to figure out what percent remains. Let me just do this. All right, so I'm going to say 15, the small amount, divided by the larger starting amount. And when I divide that, I get 0.125. That's my percent. So what I need to do is I need to check this against my half-life data table. And when I do, I can see 0.125 equals 3 half-lives. So this equals 3 half-lives. And each half-life is 20 days. So therefore, what I've got here is 3 times 20 is 60 days. Now sometimes when kids look at this, they become confused by this amount here. Well, the reality is we don't really care about the daughter isotope. It's all about, in calculating, using half-lives as a way of calculating ages, it's really about how much of the parent isotope is left. I start off with this much parent, I now have this much parent. It takes 20 days to cut it in half each time. In order to get from here to here, I had to cut it in half 3 times. And each time I cut in half took 20 days, that gives me 60. Let's see what else we got here. Let's see. All right, plutonium-242 is a product of nuclear reactors. All right, the isotope has a half-life. Approximately how long it would take for 1,000 grams to reduce to 1. So I'm going to say 1 divided by 1,000. And that should be 1 divided by 1,000 is 0.001. And if I take that half-life table, I'll see that's 10 half-lives. Now each half-life takes this long, so I just had to multiply that by 10. So I just had to say 3.76 times 10 to the 5th times 10 half-lives. So this is the length of 1 half-life. This is 10 half-lives. Well, gosh, when you do that, all that happens is the exponent changes. So this is going to be 3.76 times 10 to the 6th years. And let's look, I believe is the last one now. Nope, next last one. All right, we got carbon-14, which you might have heard of. Has a half-life of 5,715 years. So if we know bones start off with this and ended up with this, how old is the sample? So we're going to say, take what you ended up with, the smaller amount that you ended up with, divide by the larger amount you started with, 2.4 times 10 to the negative 3. And don't forget to use your EE key. Whoops, there goes the bell. And when I do that, I'm going to get 0.03125. Now I'm going to consult to see how many half-lives that is. Now remember, it was 0.3125, which basically is here. That's 5 half-lives. So we go to, so that's 5 half-lives. Now each half-life lasts 5,715 years. So I take, this is how long each half-life was, and there was 5 of them, so I'm going to multiply 5 by this. So I'm going to say 5 times 5,715 years per half-life, and that gives me a time of 28575 years. And that's how they find the date of old things. Let's look at one last thing here. It says, why do you think carbon-14 dating is unable to provide reliable dates for fossils more than 50,000 years old? And the reason is, since the half-life is this, and we're talking about very small quantities to begin with, there is too little of the original material left. Too little of the parent isotope left in order for us to determine how old the sample is.